Another effect of projection is if you want to study or find clusters using lensing, which I think is becoming clear is a very bad idea, because you get these very nasty projections. And this is a work by Joe Hanawi, which showed that in the simulation they even found a significant peak where there was nothing along the line of sight. It's just a matter of projections. And then automatically, and I think somebody showed it yesterday also, then you tend to get more or less, because you get a very nice redshift distribution for this peak, and it just has to do with the lensing kernel where it peaks. So there's really nothing here. So in the other cases there were clusters, but there are cases where there's really nothing, and the data themselves don't really tell you anything. And in particular for cluster abundance studies, what you get if you have so much contamination and so on, you get a very inefficient survey, and that's indicated here is work by Martin White, where your completeness is rather poor even at high masses, and you get a lot of contamination in your cluster survey. Another thing, so even if you look at, like say, you find clusters another way, if you want to compare masses, you have to somehow pick the center. And that turns out, if you look at very massive clusters, it's usually okay, but as you go to lower and lower mass or higher and higher redshift, this becomes progressively more complicated. Especially at high redshift, you usually don't have a single most dominant galaxy. In the X-rays, you saw several cases where you have multiple X-ray peaks, so it becomes very unclear what center to pick. But you do have to somehow account for this, because if you have the wrong center, you get the wrong mass. In particular, if you have complicated substructure, it's not quite picking the wrong center, but substructure also tends to lower your lensing signal because you're measuring a mass contrast, right? It's important to keep in mind. So here's MS1054 again, and what you see is that this lensing signal goes to 0 at these radii. So that's very strange. You might think, well, what's going on here? Well, it's just the fact that, remember, we had this complicated mass distribution. If I'm between two mass distributions, the contrast can go to 0, and so my tangential shear vanishes. And that's what is happening here. So if you fit an NFW profile to this, you basically are going to bias your masses low. And so the way to partly circumvent is use aperture masses. Basically do a one-dimensional mass reconstruction, start integrating here, integrate into some radius, and that really minimizes the model dependence and reduces sensitivity of the centroid errors. Still, you have to pick a center, but also limits somewhat the problems with substructure. In the end, that's what lensing really measures. It measures the mass within some aperture. But then if you want to compare to other probes, we somehow have to deproject it. We have to find some relation between the two. And I think also their simulations really can play an important role, but unfortunately too little has been done there. So centroiding is particularly interesting. So what we typically do, we put the centroid on the central galaxy, and so there's and you find that in many cases the central galaxy actually is a very good definition of the center. There's very little offset between the cluster center. But what we found with my student Chris Bielefeld is that if you have the most, what we think are the most relaxed clusters, they have cool cores, and those central galaxies are forming stars and actually do not lie in the red sequence. And so we'll see when you do these enormous surveys such as the SDSS, you don't really can spend the time trying to find the center of your cluster. So what they do is they pick the brightest galaxy in the red sequence, and that's a bit worrisome because your most relaxed clusters, the ones where the center is best determined, they systematically miss center because those central galaxies are not on the red sequence. So you really have to be careful in the centering. So that's sort of the introduction. Now, taking a step back and give a brief history of cluster lensing, because I think that's quite appropriate here, because although cosmic shear has always been, at least I think for many, the sort of driver to do weak gravitational lensing, the lensing signal itself was first detected behind a cluster of galaxies because that's where the signal is the strongest. And so this was first done by Tony Tyson in 1990, so we could also say 2 decades of cluster lensing. And so, yeah, so they saw this net alignment of distant sources, but of course even then, even behind a cluster, the signal is only a couple of %. So in the 90s, mid-90s, this really started picking up, although I do remember at this time lensing was still seen as an oddity. Like this was, people really were very skeptical about the results. Like, even though things looked quite reasonable, people just didn't believe he could control systematic. So in that sense, it's astonishing that now, 10 years after the first cosmic shear detection, we have this meeting and people seem to believe what we're doing. It's astonishing. Yeah, so here are these early results by Gordon Squires, Nick, of course. And so you can see the signal going up towards the center of the cluster. But at that time, cameras had small fields of view, and we didn't quite know the redshift distribution of the sources very well. So sure, there's a signal, but the interpretation is really complicated or hampered by this. So the new millennium brought a whole new approach because, of course, everybody jumped the cosmic shear bandwagon, including me. And so we got these wide mosaic cameras, and also Sloan, of course, has done wide field imaging. But it turns out that this is great for cluster studies as well, because this early work had really small fields of view where the cluster sort of fits into the field of view, but you can't really go far out. So you really sort of limited in how you can determine the masses of the clusters. But these wide field images can image clusters very well. We can image large samples out to large radii. Also, we now have a much better knowledge of the source redshift distribution, and we can have spent a lot of time correcting for systematic effects. And so all this machinery that we develop for cosmic shear, we can apply to galaxy clusters. And I would argue, as we'll see, is as the samples of clusters become more and more, become larger, actually the requirements for good cluster work are the same as for cosmic shear. If you look at a sample of 100 clusters, each cluster is detected with a signal to noise of 10, and you want to look at the scaling relation, normalization of that scaling relation, the statistical error is 1%. Right? That becomes comparable to the accuracy we want for cosmic shear, and we want to improve upon that because we already have samples of 100 clusters. So we have to deal with a lot more things. So also contamination by cluster galaxies becomes an issue. Centroiding errors, all these things become suddenly a lot more complicated, as with anything. So if you want to look at these cluster abundance studies and really learn about the cluster physics, lensing plays a very important role, as I said before, because it provides this link between the baryonic parts of a cluster and the simulations. Because the mass is really a fundamental property of a cluster. Right? So you can simulate the X-ray temperature, but if you're not quite sure if it's the right mass for that temperature, you always are in trouble when comparing to the observations. And so the role there is that lensing can calibrate the mass proxy relations, but I think what is more important or equally important is measure the intrinsic scatter in these relations, because that really requires an independent measurement of the mass of a cluster. Because when you do cluster abundance studies and do cluster cosmology, the scatter is a very important parameter. It's often ignored, but as the samples increase, this has to be included. So we have two options to study clusters. So I've taken more or less this approach, study masses of individual clusters, because that allows us to study the scatter. But the downside is that it's expensive. We have to get lensing grade data for large samples of clusters, and we can only do massive clusters of galaxies. The other approach is take ensembles of clusters, and being Dutch, it's still very appealing because it's cheap, and you can do a large range in mass. That's very important. So you can, it's very complementary because you can study a much larger range in mass, but questions are how would you bin? Like this is very important. It's not obvious. And here you can also spend time to try to figure out what is the best center. Here you don't have the manpower or resources to do that. And it's very difficult to really nail down the intrinsic scatter. There are ways to do it, but it's still limited. You have to make all kinds of assumptions. So stacking, I'll start with that, is very useful because we can study low mass systems and measure signals out to very large radii. So we can, as I said, that's very complementary.